In this video, we will discuss the trapezoidal rule and its uses. Sometimes it's difficult to integrate certain expressions exactly. Because of this, different methods have been devised to help us approximate the value of definite integrals. In some of these methods, we approximate by using rectangles to estimate the area under a curve. The trapezoidal rule, however, uses trapezoids to do this. Recall that the area of a trapezoid is 1/2 times the height times the sum of the bases. The rule states that given a function that is continuous over an interval a, b, we can break this interval down into n trapezoids of length delta x. These trapezoids will have endpoints at x sub 0, x sub 1, out to x sub n. We can then set the combined area of the trapezoids, t sub n, equal to 1/2 delta x times the quantity f of x sub 0 plus 2 times f of x sub 1 plus 2 times f of x sub 2, all the way out to 2 times f of x sub n minus 1 plus f of x sub n. Using this, we can say that the limit as n approaches positive infinity of t sub n is equal to the integral from a to b of f of x dx. We'll use this integral to approximate the area under a more complicated curve. Let's try an example of this. Here we are given the definite integral from 2 to 3 of 3x cubed minus 2x plus 1 dx. We can see here that a is equal to 2 and b is equal to 3, so our interval is from 2 to 3. We'll break this up into 4 subintervals to use the trapezoidal rule. This means we will have n equals 4. Knowing this, we can find delta x. So we have delta x is equal to 3 minus 2 over 4, which equals 1/4. To find the endpoints of each trapezoid, we'll start at 2 and add delta x until we reach 3. This gives us p equals the set containing the values 2, 9/4, 5/2, 11/4, and 3. Now we can set up our equation. Using the trapezoidal rule, we have the integral from 2 to 3 of 3x cubed minus 2x plus 1 is approximately 1/8 times the quantity f of 2 plus 2 times f of 9/4 plus 2 times f of 5/2 plus 2 times f of 11/4 plus f of 3. Now that we have our equation set up, we can evaluate it to approximate the integral. Start by evaluating the function at each of the endpoints. This gives us 1/8 times the quantity 21 plus 61.344 plus 85.750 plus 115.781 plus 76. Performing the addition and multiplication, we have approximately 44.984. If we were to perform the integration by hand, we would see that the exact value, rounded to 3 decimal places, is 44.750. We can see already that these are pretty close, but let's calculate the absolute and relative errors to see just how close they are. To calculate the absolute error, we want to take the absolute value of the difference between the exact answer and the approximate answer. So we have the absolute error is the absolute value of 44.750 minus 44.984, which equals 0.234. Now we can calculate the relative error. Divide the absolute error by the exact value. This gives us 0.234 divided by 44.750 equals 0.0052. As a percentage, this would be 0.52%, which is pretty small. Since the error is so small, we can conclude that this is a good method of estimating this integral.